This presentation will look at electrical energy and the measuring of current and voltage and what each of those are. Just as a bit of a revision, electricity is really the result of electrons being moved in a material. There's two types of electricity: static, which really stays in the one place, and current, which involves moving electrical charges. Static electricity builds up in one location, and you can see it when you get static electricity builds up on you yourself, and you either get a zap when you're getting out of the car or going down a slide or something like that. And current electricity, where electric charges are moving, and this is the sort of electricity that you're used to when you plug in an electrical device and then runs by electricity. That's because that moving charge is current electricity. And the current electricity, as we said, is where electrical charge is actually moving. Now, metals are the best conductors of electricity, and that's because their electrons aren't tightly bound to the atoms and they can move from one atom to another, which means that that movement of charge then is easily produced in a metal. Electrons, as we said, flow from one atom to another in metals and allow that charge to move, which is called electric current. Now, the amount of electricity that's measured by how many electron charges goes past a particular point in an electrical circuit. That's what we're measuring in this case. We're measuring the amount of charge that moves around a circuit, but we're measuring it perhaps at a particular point. And the amount of charges that pass a particular point in an electrical circuit is called the current. So they're really counting how many charges go past. And that's measured in amps. The more current that is in an electrical circuit, the more charge is in the electricity. Now, to measure that, we need a device called an ammeter. We've got one here with the big A on. And it is put actually in the circuit, in series if you like, or you can follow the wire from the red positive terminal through the globe and then through the ammeter and then back into the negative terminal as the power supply, and that will measure the amps or the current or how much charge is moving around that circuit. So, as we said, an ammeter is used to measure that. And if we do a circuit diagram of what we've got here, it would look like this. Again, we've got our battery or our power source going to our light globe. That's the two little lines with the squiggly line in between. And then that goes to a circle with A, which represents our ammeter, and that goes back to our battery or power source. Now, there's a different property we can look at electricity, and that's to do with how much energy is given to each electrical charge. So it's a bit like the power source revs up your charges and gives it a particular amount of energy and then sends it around the electrical circuit. The amount of energy that's in each electrical charge is called the voltage, and it's measured in volts. And the voltage is measured with a voltmeter. So here we have a voltmeter set up, and you can see our circuit. It's got our power supply again. It's got a little globe there. But instead of having the voltmeter in line with the globe in the circuit, it's actually piggybacked on the globe, and it's called a parallel connection. So, as we said, the voltmeter is connected in parallel to an electric circuit to measure voltage. And if we're looking at the circuit, it would look like this. Now you can see we don't have one little track, if you like, going through the light globe and then through the voltmeter and then back to the power supply. We actually see that we've got the voltmeter piggybacked on the circuit where the globe is, and that's how you measure voltage. when we're looking at sources of power, we can get electric supply or power from a number of these sources. The first one is obviously power stations, and they generate power by turning turbines, and that's through the burning of coal or gas that fires up a boiler, which then puts steam in, which turns a turbine, or it can be through running water, and the hydroelectric scheme in the Snowy Mountains, or in the Hume Dam in Albury, or there's quite a few in Tasmania, where big rivers send their water or some of their water into the power station, and that huge amount of rushing water then turns these turbines, which then generates electricity. Another way of getting power is through batteries. Now, batteries supply power through a chemical reaction. And photovoltaic cells, or solar panels if you'd like to call those, produce electricity by the action of light on the chemical in the panel, and that actually generates electricity. So if we have a look at batteries, there are two types. The first one is a wet cell. The wet cell contains an acid as a liquid. In this one here, which is an example of a battery you might find in a car, or sometimes people store power from their photovoltaic cells in a battery, then often it's this sort of battery. This is what's called a lead acid battery. It's a wet cell because it contains a sulfuric acid as the liquid, and the metal in the battery is lead, and the electricity flows from the negative to the positive electrode. Then we can have what's called a dry cell. These are the ones you're used to put into your devices, and they're the AAAs and AA's and C's and D size batteries. A dry cell has either a carbon or metal rod in the middle of it, and that's surrounded by chemicals, which are also often mixed with a catalyst. The chemical reaction then in the battery produces electricity. Photovoltaic cells these are the panels that people put on the roof to generate electricity. When the sunlight comes on the roof, the chemicals inside will generate electricity, and that can be collected. Now, there's some other properties to electrical circuits we can talk about. The first one is resistance. And this is a measure of the energy that's lost by charges as they walk around or as they move around the circuit. Some substances have a very little resistance, and so it's really easy for electrons to travel around. And something like a metal, for instance, would have very little resistance. Whereas something like a plastic or rubber would provide very high resistance, or other materials, and that means that when the charges go through that, they lose energy because of the resistance to the material, and this is what's called a voltage drop, because they're losing energy. If you think about when you're walking out in the open, it's pretty easy to walk in the open, but if you go down to the beach or get into a pool and start walking, then it becomes a lot harder. So the resistance is higher. And then you might imagine yourself walking through a swimming pool full of porridge, and that would be even more harder. So even more difficult. So that provides a higher level of resistance, and you use more energy by having to push through that. So if you think about the voltage drop as the loss of energy of something going through a material that's difficult for charges to travel through, then you'll note that there is this loss of energy. By the way, even when charges go through something like an electric light globe, the globe glows, and the reason it glows is because it gets hot. Why does it get hot? Because there's a resistance there, and so the charges are losing their energy, and it's becoming light energy, so you can see, and also heat energy, because you know that globes are hot when they've been on for a while. We can also talk about conductors and insulators. We have already talked about a conductor as a substance that will allow electricity to travel through it, and it's got very little resistance. And good examples are metals or water with ions in it. If you get absolutely pure water, it doesn't transmit electricity very well. But if you dissolve something like salt in it, for instance, there's ions then, and those charged ions can then help transmit the charges from one connection to another, and that means it will allow electricity to travel through the water. An insulator is something that's got a very, very high resistance, and that electricity charge basically doesn't go through it. Examples are plastic and rubber, and you know that electrical wires have the plastic coating around them, and that's because it insulates them from other wires and any other material or other connections that might short it out. If you have a as we were talking about with the insulators, so if you look on electric power lines and see that there are ceramic insulators, they're those red or white solid things, little circle type things that are on the power lines. They're there because they don't allow electricity to go through, and they insulate it. So it's important to think about insulators and conductors, what they are, and the relative resistance of each one of them.